So here's the process real quick. So process for graphing a function. This is the order I usually go in. Step one, intercepts. So y and x. Y, you set x equal to 0. X, you set y equal to 0. The second thing, asymptotes, if any, right? Vertical asymptotes, you're usually looking for where the denominator is equal to 0. The only other kind of exception to that is, or if you have a logarithm somewhere, it's a little more, it's not quite as straightforward as just you have a log. Like there are some functions like x times natural log of x where you don't actually have a vertical asymptote at 0. We'll talk about that in a minute. I suppose even, so maybe I should back up a little bit. I suppose what we should really think about first is, so step 0, domain. It's definitely worthwhile to, if not explicitly writing down the domain in the beginning, at least thinking about what is my domain? Because if you have something like x natural log of x, your domain is everything greater than 0. Okay, so asymptotes, vertical asymptotes, you're saying the denominator equal to 0. Horizontal asymptotes, there are various ways to find them. The most general way of saying it is you're actually taking the limit as x goes to either infinity or negative infinity. Sometimes this can be quite complicated. All right. After I've done the intercepts and the asymptotes, I deal with the first derivative stuff. And I usually just like to make a first derivative sign chart. So right, this involves finding the critical values, putting them on the sign chart, and then seeing where the first derivative is positive and negative. Because that gives you the whole idea of how the graph looks. So like, typically, sorry, my computer is telling me to do a thing. I'm like, no, I don't want to do that thing. Okay. So right, typically we've got like critical value, and the derivative is like positive, negative, positive. So we know the function's increasing, decreasing, right? If you got something like that, that tells you a lot of information. It tells you have a relative maximum there, a relative minimum there, assuming the function is defined there. And it also tells you the shape of your graph. And then lastly, which we haven't talked about, at least I haven't talked about with you guys, is the second derivative stuff. So again, that's going to mean finding the critical values for the second derivative, finding where the second derivative is positive or negative, and then seeing what we've got. So we might end up getting something like, one critical value for the second derivative, and it being, positive here and negative here, which means it's concave up and then concave down. And then you have an inflection point when the concavity changes. One thing I will say, I'm going to say a million things. One thing I'll say right now, a thing I will say about concavity is that when the concavity changes, you get an inflection point. It doesn't matter which way it changes, meaning if you're going from left to right, it doesn't matter if it's positive to negative or negative to positive, you still get an inflection point. Whereas with the first derivative stuff, if it changes from positive to negative, you have a relative max. If it changes from negative to positive, you have a relative minimum. So it does matter for the first derivative if you're going from positive to negative or negative to positive. Okay. So let's start off with, so we're going to start including all the second derivative stuff, and I will tell you sometimes it's going to be ugly. The second derivative is just not always nice. But we're going to do lots of examples. Let's start off with an easy, nice polynomial example. So let's look at, oh, sorry, I had one off. I had one all lined up in my brain. Yeah. So the words I'm not writing here are graph the function, find all the stuff. Find all the intercepts, asymptotes, relative maxes, relative mins, where it's increasing, where it's decreasing, inflection points, concave up, concave down. Right, that's all the stuff. I don't want to write that down. So you guys, we're finding all this stuff. Okay. So first things first, let's find the y-intercept. So y-intercept, I'm setting x equal to 0. F of 0 is clearly 0. X-intercept. Setting y, or the function, equal to 0. So 0 equals x to the 4th plus 4x cubed. And typically well, maybe not typically, but a lot of times you're going to be able to factor. I can factor out an x cubed here. So 0 equals x cubed times x plus 4. So I'm getting x equal to 0, x equal to negative 4. That, I can draw a 4. Really, I can. Sure, that's a 4. This function, being a polynomial, has no asymptotes. Polynomials never have any vertical or horizontal asymptotes, so we can move on from there. No asymptotes. Great. I will also mention, just as a quick aside, Desmos is a very useful tool. I would encourage you all to make sure you're familiar with it so that when you have to graph something that's maybe super complicated, although you're still maybe expected to do it on your own, you can still at least at some point look at the graph on Desmos and be like, okay, I did a reasonable job of doing that. But like, it's nice to be able to look at a nice graph of the thing you're actually trying to graph and say like, okay, yeah, I see what is happening with this. So I would really, really encourage everyone to familiarize yourself and use the tools that are available to you when allowed. So we did the intercepts, no asymptotes. Let's move on to the first derivative stuff. So first off, we're going to find the critical values. So we're going to take our derivative, which is 4x cubed plus 12x squared, and set equal to 0. And it's going to be easier to find our critical values if we factor. So I'm going to factor out an x cubed. Sorry, I'm going to factor out a 4x cubed times, let's see, the 4x cubed, come on, James, a 4x squared maybe? Yes, a 4x squared. Also, if you guys have particular questions, you're welcome to ask or write them in the chat, or you're just welcome to be along for the ride. So I got 4x squared times an x here and a 3 there. So my critical values are x equal to 0, and x equal to negative 3. And then there are many ways of doing this, but I personally think it is best to put the critical values for the first derivative on its own sign chart or number line, whatever you want to call it, in the right order. Right? Smaller numbers to the left, bigger numbers to the right. And then we want to see what the first derivative is doing. So I'm literally just going to pick points. And I will say it is also really beneficial to have it factored, because if you try and pick one, well, okay, one's easy. If you pick one and plug it in here, it's like, okay, it's positive. If you pick like negative 2, it might not be clear if it's negative or positive, because if you plug in negative 2, this part's negative and this part's positive, and you add them together, you actually have to think about which is bigger. Or you can do it the smart way and plug in negative 2 here and say, oh, this part's positive, the whole darn thing is positive. Or you could use the method that asks us to look at the multiplicity of the factor that the 0 came from. The multiplicity is even, the sign stays the same. If the multiplicity is odd for the factor that the 0 of that factor came from, the sign changes. Or you can pick a point. Negative 4 squared is positive, negative 4 plus 3 is negative, positive times a negative is negative. And then I really like to also draw what the graph is doing. Oh, the graph is decreasing, or I should say the function, right? The function's increasing, the function's increasing. So doing that really gives me a good idea of what this thing's gonna look like. In fact, a lot of the time, I tell people that you can just start drawing the function now, right? I know, if I can let us start drawing the function now. The only problem with drawing the function now, before I talk about the second derivative stuff, is it might not look like my second derivative details line up where they actually should be. Okay, so let's see, drawing a function. And let's see, what do I got? I've got y-intercept at 0, x-intercept at 0, and negative 4, and negative 4. So I've got x-intercepts there. And I also have, here's an important thing to say. So I have critical values at x equals -3 and x equals 0. I didn't talk about the relative extrema. So do I have a relative maximum? Yes or no? You guys can click the little buttons. Ooh, I like the little buttons. You guys can click them. I like these little buttons. Oh, did I just? That's weird. Oh, I thought I clicked it for someone else. It's like, okay, yeah. It does not. There's no relative maximum, but it does have a relative minimum at -3. So we have a relative, or local, if you prefer the word local, a relative minimum at x equal to -3. Now, since we're going to try and graph that point, we should also find the y value. So I should plug that -3 back into the original function. And this is where it's going to be really good to have the original function factored, because it's a lot easier to plug in -3 here than it is to plug it in there. So I'm going to say, okay, the y value, f of -3 is -3 cubed times -3 plus 1. Oh, sorry, -3 plus 4, which is 1. So my relative minimum is the point x is -3, y is -27. So somewhere down here. Clearly my graph is not to scale. But now I know that before I get to that point, it's going to be decreasing. I'm going to get to that point, it's going to be increasing, and then I'm going to get to 0, it's going to be increasing after that. And at 0, it's probably going to level out for a second, right? The derivative at 0 is 0, so it's going to probably do something like this. It's going to be decreasing, increasing, and it's going to be increasing afterward. I'm going to have to level out. So it's probably something like that, like that. That's what happens when you have like increasing on either side of a critical point, is it kind of flattens out at that critical point like that. I kind of think of it as like the x cubed function, right? Y equals x cubed, flattens out right there at that critical point at 0. Same kind of idea over there. Okay, but now we should talk about the second derivative stuff, because there are definitely some inflection points. Ooh, actually, okay, so back up. I would never ask you to tell me where it was increasing or decreasing, but I am not your professor. Your professor might ask you to state the intervals where it's increasing or decreasing. So we can say it's decreasing on the interval where the derivative is negative, so decreasing from -infinity to -3. And it's increasing. Now, if it's increasing, we exclude the point if the function's undefined there. We include the point if the function's defined there. This function's defined everywhere, so we definitely include that. So it's increasing on the interval from -3 to infinity. Again, I don't think that's something you need to write down if you're just graphing it, but I know there are some web work problems where they're like, tell us where it's increasing, tell us where it's decreasing. So you're just looking at the sign chart and seeing, okay, where's the derivative negative? That's where it's decreasing. The function's decreasing. Where is the derivative positive? That's where the function's increasing. So now let's talk about the second derivative test. The second derivative stuff, which is not the second derivative test. We can talk about that test if you guys want to. The second derivative stuff is all about the concavity. So I'm going to take the second derivative. Reminder that my first derivative was 4x cubed plus 12x squared, right? Right. I will say, so it's often easier to use the factored form to like solve for things and plug things in, but it's usually better to use the unfactored form to take further derivatives, right? I don't want to use the product rule to take that derivative there. So second derivative, let's see, derivative that's going to be 12x squared plus 24x. I'm going to set that equal to 0. I'm finding the critical values for the second derivative. So, sorry, brain, factor out of 12x. And I don't know why, but I've seen a number of people make the mistake recently where they factor out 12x from something like this and they get x plus 12. For some reason, people are like factoring out a 12 and getting another 12 here when it should be a 2. I think they're thinking it's like 12 plus 12 is 24, but really, it's 12 times 2 is 24. Anyway, just be careful. And then we're going to get x equal to 0, and x equal to negative 2. So putting those on the number line, right, I'm looking at what the second derivative is doing. So over here, when x is positive, 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 positive. When x is negative 1, let's say, that's going to be negative, that's going to be positive, so the whole thing is negative. And when x is negative 3, negative, negative makes the whole thing positive. So if the first, so I'm going to add in a line that I don't normally add in, but let's not get there for you. So if the second derivative is positive, the function is concave up. If the second derivative is negative, the function is concave down. Positive, it's concave up. I'm also going to mention, and I'm going to say more about this after this example, that if the second derivative is positive, the first derivative is increasing. It's not something we really need to know at all graphically, but it is something I want to talk more about. And here the second derivative, or the first derivative would be decreasing, and here the first derivative would be increasing. But I don't usually draw that when I'm graphing these things, so don't worry about that. So we have, if you want to talk about intervals of concavity, it is concave up on the interval from negative infinity to negative 2, union 0 to infinity. It's concave down on the interval from negative 2 to 0. We definitely have inflection points at 0 and negative 2. So where can I write that? We have an inflection point at, when x is 0, we know the y coordinate is also 0. So inflection point is 0, 0. We also have an inflection point at when x is negative 2, whatever f of negative 2 is. Which is negative 2 comma, let's see, our original function was x cubed times x plus 4. So we plug in negative 2. We get negative 2 cubed times negative 2 plus 4, which is negative 8 times 2, which is negative 16. So our inflection point appears to be, so like if I try and actually make it look where my graph is, it looks like it's maybe right about there. Okay, that's, it doesn't look quite right. I can fix it though. So this is where like maybe I wouldn't actually draw it ahead of time. Okay. So yeah, so inflection point. And then we have an inflection point also right here. And the inflection point is where the concavity changes. So there's a couple ways to think about concavity. So from here to here, it's concave up. It's opening upwards. From here to here, it's concave down, it's opening downwards. From here onwards, it's concave up. A couple other ways to think about that is from here to here, if you think about like that we're looking like at a topographical map and this is like a road, and if you have a car driving on this road from left to right, so if we drive this way, we are turning ever so slightly, right? Our car is turning, sorry, I'm going to draw a car here. There's my car with like 4 little wheels on it, and my car is turning to the left, ever so slightly. I mean, when I get down here, it's going to make a real sharp left turn. But it's turning left, and then when I get to the inflection point, the direction the car is turning is changing. It stops turning left, it starts turning right. So turning right, turning right, turning right, turning right, up until this point, and then I start turning left, turning left, turning left again. And literally, if I keep going this way, I'm turning left forever, just a very, very slight left. Kind of like you're driving on a road and you're turning a very slight left to make sure you don't go off to the right because our roads are slightly that way.
Limits to, how about infinity and negative infinity?
Sorry, say that one more time.
What about limits like from going from negative infinity? Good
question. I'll address it in one moment.
Yeah.
The other thing I want to point out here, though, is another way to see this is when you're concave up, it's when your first derivative is increasing. If I start way over here, my first derivative is super duper negative, right? Slope of the tangent line, super negative. And then as I move this way, my first derivative is less negative, 0, slightly positive, more positive, as possible at the inflection point. At least as positive as possible for this particular function in this part. And then it starts becoming less positive. So now it's decreasing. So here the first derivative is decreasing. It's concave down. The second derivative is, negative. So first derivative is decreasing, and then we get to here, and then the first derivative starts increasing again. So that's why I said this thing here. The function is concave up. The first derivative is increasing. The second derivative is positive. Those all mean the same thing. Or the function is concave down. The first derivative is decreasing. The second derivative is negative. Those all mean the same thing. To answer the question about limits to infinity or negative infinity, so the reason I wrote those down is because that's how we find horizontal asymptotes. Here, that's not going to produce anything other than saying, well, if I take the limit to infinity, I'm going to get infinity. If I take the limit to negative infinity, I'm also going to get infinity. And you can see that if you factor the first function. Right? If you look at this x cubed times x plus 4, you can see that as x goes to infinity, you get infinity times infinity. And as x goes to negative infinity, you get negative infinity cubed, which is negative infinity, times negative infinity plus 4, which is negative infinity, and then negative times negative is positive. So as x goes to negative infinity, you also get positive infinity. But really, the reason I wrote those limits is really as a reminder that that's how we find horizontal asymptotes.
All right, thanks. And it is also very important, though, to know how your function is behaving at those endpoints.
Correct. It's just that we don't really need to write that down for a polynomial, because once you got the sign chart here, we know what's happening. We know that, you're coming down like that from the left, and you're going up like that to the right. And for polynomials specifically, you are always either going to infinity or negative infinity at the ends. Okay, let's do some more. Oh, actually, I should talk, again, I'm going to say a few words about concavity real briefly. So concavity, so if you got something like this, and I'm thinking of like kind of just a parabola, right? This is definitely concave up. Sure, I can write the words. And so when I think about being concave up, I think about literally three things. I think about the function is concave up. But like I was saying previously, I also do think about the first derivative is increasing, right? As I move from left to right, my slopes of my tangent lines get larger and larger and larger, or less negative, right? Super negative, less negative, 0, more positive, super positive. And then that's also the same as saying the second derivative is positive. And we kind of know that's true, right? I'm gonna cover this up for a second. We know that if something is increasing, its derivative is positive, right? That's how we find what the first derivative is, right? We want the function is increasing when the derivative is positive. Well, the function is increasing when its derivative is positive. Or the first derivative is increasing when its derivative, the second derivative, is positive. And then you can also have something concave down, and you essentially got the same stuff going on, right? F of x is concave down. And you can say that the first derivative is decreasing, right? It's starting off super positive, and then less positive, and then 0, and then negative, and then more negative. And then we could also say that the second derivative is negative. So I would really, 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 really like for all of you to understand that these three things all mean exactly the same thing. These are all equivalent statements. If one of these is true, all of them are true. If one of these is true, all of them are true. And then the fun part, concave up, like a cup. Concave down, like a frown. This makes it easy to remember. I mean, concave up, concave down isn't that hard to remember on its own. Concave up, you're opening upwards. Concave down, you're opening downwards. And I usually think of concave up as like y equals x squared, and concave down as like y equals negative x squared. Those are my prime, in my head examples. All right, let's graph some more things. And yeah, let me grab an example that I know is good to go. Let's see, do I want, yeah, I do want you. Sure, okay. So let's look at this example. Let's look at f of x equal to, yeah, you're gonna be gross, but fine. X squared minus 8 over x minus 2 squared. Whew, all right, looks hot. So, I've only said so like probably a bajillion times this week. All the things. Y-intercepts. Set x equal to 0. F of 0 is negative 8 over negative 2 squared is 4. Negative 8 over 4 is negative 2. X-intercepts. For a rational function or any kind of fractional thing, to find the x-intercepts, you could set the whole thing equal to 0, but we know we're really just setting the numerator equal to 0. So set x squared minus 8 equal to 0. You could factor that. Yeah, you could factor it. It's kind of ridiculous, but you could factor it as x minus the square root of 8 times x plus the square root of 8. Or you could just add the 8 over and say x squared equals 8, x equals plus or minus the square root of 8. So 2 x-intercepts. Now let's find the asymptotes.
Oh, one quick thing.
Go ahead.
The domain function, f of x doesn't equal 2 or negative 2.
Well,
right?
I would say this, so the domain is not what f of x can't equal, it's what x can't equal.
Oh, okay.
Specifically, the domain here is x can't be positive 2, but it could be negative 2.
Okay, yeah, right.
Okay. On the other hand, if it was x squared minus 4 in the denominator, that would be where x couldn't be plus or minus 2.
Okay.
And you're right, I should have looked at the domain first, but often when it's a rational function, I know that I'm going to get to like the domain part when I get to the vertical asymptote part.
Okay. Thanks.
Yeah, of course. But you're right. Like it's always good to think about, oh yeah, what's my domain here? So for the vertical asymptotes, we're just seeing where the denominator is 0. So x minus 2 squared equals 0. So x equals 2. So that's my vertical asymptote, x equals 2. And yes, x equals 2 is not in the domain. And finally, the horizontal asymptote. Now let's go up here. So this is where I say the thing about taking the limit. So really, when you're finding a horizontal asymptote, what you're actually doing is you're taking the limit as x goes to either plus or minus infinity. For a rational function, it's the same on either side, so we don't have to look at both sides. So limit as x goes to infinity of x squared minus 8 over x minus 2 squared. Can anyone type in the chat and tell me what this limit's going to be? Without using L'Hopital's rule? I know you all know how to do this. I think you've just forgotten that you know how to do this. Or you just don't want to write anything in the chat. Yeah, it's a 1. And the way you know it's 1, or one of the ways you know it's 1, is that if you multiply at the bottom, right? If you multiply at the bottom, it's a little easier to see. You have x squared minus 8 on top, and x squared minus 4x plus 4 on the bottom. And now we know, oh yeah, I've got a rational function. And when you have a rational function, if the degree on top and the degree on the bottom are the same, then the horizontal asymptote is the quotient of the leading coefficients, which is 1 over 1. Now you could use L'Hopital's rule if you had it, but you don't, so you shouldn't. Or you could do more work and divide everything by x squared, which is really what we're doing when we say this. We're just not showing the work. We divide everything by x squared. It's the limit as x goes to infinity of 1 minus 8 over x squared over 1 minus 4 over x plus 4 over x squared. This goes to 0, this goes to 0, this goes to 0, you get 1 over 1. But for a rational function, you really should just be able to say, oh, I know it's the quotient of the leading coefficients if the degrees are the same. All right. So really, if someone said, what's the horizontal aspect of this? Almost anybody would be fine if you just said, oh yeah, I know the horizontal aspect is y equals 1. Because I know I've got an x squared over an x squared, and those are my highest powers on the top of the line. There are other functions where it's more complicated, specifically ones involving e to the x, and we'll try and do one of those today for sure. All right, so now it's going to get messy. Now we got to find the first derivative and the second derivative stuff. And the first derivative of this is not going to be very nice. Sometimes, if a teacher wants you to graph a rational function on a test, some of the times they'll actually give you the first derivative and the second derivative so that it's more a test of your graphing ability, not a test of your differentiating ability. But let's find the derivative here. So we're going to use the quotient rule. The derivative is going to be the bottom times the derivative of the top, which is 2x, minus the top times the derivative of the bottom, where we have to use the chain rule. It's going to be 2 times our stuff to the first power times the derivative. Okay, the derivative of stuff is just 1, so it's not a very exciting chain rule. All over x minus 2 to the fourth. I think I was saying this last class, although it might have been a different class. When you've got a quotient rule and your denominator is already to a power, you're always able to factor out some of that in the top when you take the next derivative. Or another way of saying this is, I know that when I take the derivative of this and I simplify it, I should end up getting x minus 2 to the third in my denominator. Basically, when you differentiate something that's a quotient like this, the power of the denominator just gets 1 larger after you simplify things. So I've got a 4, but I should be able to simplify it down to just having 3. Meaning I should be able to factor out an x minus 2. Oh, I can factor out an x minus 2. So let's see what I've got here. I factor out an x minus 2. And it's really important, right, because we're trying to solve this equal to 0 or undefined. Okay. So I factor out an x minus 2. I'm left with an x minus 2 to the first times a 2x. I probably could have also factored out a 2. Let's factor out a 2 as well. Why not? So I've got an x minus 2 times x, and here I've got a minus x squared minus 8. I factored out that 2, I factored out that x minus 2. Okay. Cancel 1x minus 2 with 1x minus 2. Oh, look, I got a 3, like I said I would. Now I'm going to simplify the rest of this. So this is equal to 2 times x squared minus 2x minus x squared minus 8. X minus x squared plus 8. All over x minus 2 cubed. Whew. Cancel the x squareds. This is 8 minus 2. I can factor out another 2, I suppose, and write it as another 2 would give me a 4, and it would be a minus x plus 4 or a 4 minus x. Oh boy, that was a lot of work. Okay, now everybody, what's my critical value? What makes this top part 0?
4.
Okay, are there any other critical values? Well, kind of. X equal to 2, we should include. Yeah. So I'm going to draw my sign chart up here. Okay, so I've got 2 because it makes the derivative undefined, and 4 because it makes the derivative 0. Okay, so pick a number larger than 4, like 5. Plug it in. Top is negative, Bottom is positive, the whole thing is negative. And then you can say that at 4, the factor has an odd multiplicity, so the sign's going to change. And at 2, the factor it came from has an odd multiplicity, so the sign's going to change. Or you could plug in points. You plug in 3, top is positive, bottom is positive, it's positive. Plug in 0, top is positive, bottom is negative, so the whole thing's negative. So that means my function is decreasing, increasing, decreasing. Okay, so let me ask you guys. Do I have a relative minimum at 2? Yes or no? Okay, I'm a fan of the things. I saw a yes and a no. So the answer is no. And the reason I don't have a relative minimum at 2 is because what's really happening at 2? Oh yeah, there's a vertical asymptote at 2. The function is undefined at 2. We can't have, right? That's why I tried to talk about the domain, like Will was saying in the beginning, right? The domain doesn't include 2, so we can't have any relative extreme at 2. But really what's happening is, right, we have a vertical asymptote at 2. So our function is going to go down to negative infinity and then come back up from negative infinity like that. All right. So at this point, we could graph most of the thing. Oh, yeah, okay, fine. So let's see what we've got here. So we have a vertical asymptote at 2. We have, I forgot what my stuff was. We have a y-intercept of -2, x-intercept of plus or minus √8. So y-intercept of -2. √8 is just a little bit smaller than 3. So my x-intercepts are a little bit smaller than 3 and a little bit not as negative as -3. Okay. And then what else did I have? I had a horizontal asymptote at 1. All right. And then I also have some relative extreme, all relative extrema. So I know I didn't say it. We do have a relative maximum of 4. So the max at 4 comma f of 4. Right? We're not plugging back into the derivative because that would give you 0. We're plugging back into the original function. If I plug in 4, I get 16 minus 8, which is 8, over 4 minus 2 squared, which is 4. And check that again. 16 minus 8 is 8. 4 minus 2 is 2. 2 squared is 4. 8 over 4 is 2. So I have a relative maximum at 4, 2. Right there. And we can probably draw the whole function at this point, right? Because we know it's decreasing, then increasing, then decreasing. It's going to look like this. Oh, look, we crossed the horizontal asymptote. That happens sometimes. Now for the fun part. Second derivative stuff. All right, let me ask you guys. No, I'm not even going to ask. I'm just going to do it. I was going to ask if you wanted me just to say what the second derivative was, but I'm not going to do that. So remember, our first derivative was this. Our first derivative is 4 times 4 minus x over x minus 2 to the third. So we're going to use this to find the second derivative. So the second derivative, and let's be smart about this. Let's just factor out the 4, right? Let's just think of the 4 as being way out in front. So then we take the derivative of the derivative. The 4 is just going to hang out, and we'll use the quotient rule on this part here. So using the quotient rule, it's going to be the bottom times the derivative of the top, which is -1, minus the top, times the derivative of the bottom, which is 3 times x minus 2 squared, all over the bottom squared. X minus 2 cubed squared is x minus 2 to the 6th. And I can factor out an x minus 2 squared from each of these. So I get 4 times x minus 2 squared times, so from here I'm left with an x minus 2 times negative 1. And here I'm left with a 3 times a 4 minus x. All over x minus 2 to the 6th. I can cancel those two x minus 2s, 2 of those. Oh, look, that thing I said before is still true, where when you take the derivative of something like this, it's a quotient, the power ends up just getting 1 larger after you simplify. So if I took the derivative of this, which I'm not going to do, but if I took like the third derivative, I know I would end up with an x minus 2 to the 5th in the denominator once I was done simplifying things. So let's see what we've got here. Let's say I've got this 4 times, this is going to be, let's see, negative x plus 2 minus 12 plus 3x, all over x minus 2 to the 4th. So simplifying things, I've got 4 times 3x minus x is 2x. 2 minus 12 is negative 10. And I can factor out a 2 from there. So really I've got 8 times x minus 5. All over x minus 2 to the 4th. Whew. All right. So my critical values, well, my real critical value is 5. My pseudo-critical value is 2. So here's my number line for the second derivative. And I can see that if x is bigger than 5, like 6, positive or positive, so it's concave up. If x is between 2 and 5, like 3, negative or positive. And if x is less than 2, like 0, it's a negative over a positive still, so it's still a concave down. And that should match up with our graph, right? Look, our graph is clearly concave down until we get to some point over here where the concavity changes to being up. So this point here is 5 comma f of 5. We should probably find the y value of that inflection point. So we have an inflection point at 5 comma, let's see, f of 5 would be 25 minus 8 is 17 over 3 squared is 9. Just slightly less than 2, which is the value of our maximum. There. All right. That's super fun. I didn't say it, but I should point out, right, the interval where this is concave down would be negative infinity to 2 union 2 to 5, right, because you can't include 2 because you have a vertical asymptote there. Be concave up from 5 to infinity. Similarly, it would be decreasing from negative infinity to 2 and increasing from 2 to 4 and then decreasing from 4 to infinity. Questions about this? About any of this? All right, let's do another fun one. We can do that one. That one's super fun. Yeah, I think we will do that one. That one's the kind of the least awful of the bunch. Okay. Let's try graphing x to the 4th times e to the x. E to the x, e to the negative x. It's really essentially the same, but it's a little more interesting that way. Okay, let's do all the things. Y-intercept. Plug in 0. So if I plug in 0, I get 0 times e to the 0, which is 0 times 1, which is 0. So x equals 0 gives me y equals 0. X-intercept. Set the whole dang thing equal to 0. So if I set x to the 4th equal to 0, I just get x equal to 0. If I set e to the negative x equal to 0, do I get anything? I do not. Right? E to the negative x, if you think about the graph of e to the negative x, it never equals 0. It never crosses the x-axis. It has a horizontal asymptote. So e to the negative x does never equal 0. No solution there. All right. So we only got one intercept. It's the origin. Super exciting. Asymptotes. And I suppose, so usually it's when I get to the vertical asymptote, I start asking myself about the domain. Oh, what's the domain of this function? Well, there's no domain issues, right? There's no square roots. There's no fractions. You could argue that there is a fraction. I'm going to say there's no square roots, there's no fractions, there's no logarithms. You could, if you wanted to, write this as x to the 4th over e to the x. But we know that e to the x is never equal to 0, so there is no place where this is undefined. So there's no vertical asymptotes. And horizontal asymptotes, well, we can talk about them briefly, but I feel like, we'll come back to this. Because a lot of graphs that have a horizontal asymptote that's hard to find, if you can use kind of the constraints of the graph to say, oh, I kind of have to have a horizontal asymptote. So that's what I'm going to do, and then we'll talk about how you find a horizontal asymptote here. So let's talk about the first derivative stuff. First derivative, so f prime is going to be 4x cubed e to the negative x plus x to the 4th times e to the negative x times negative 1. Right, derivative x to the 4th times e to the negative x plus x to the 4th times the derivative of e to the negative x, which is e to the negative x times negative 1. So let's see. I'm going to factor because I'm trying to find the critical value. So I'm always going to try to set this equal to 0. So I can factor an x cubed e to the negative x. I'm left with a 4 here, and then x times a negative 1 there. So it looks like my critical values are what? What's one of my critical values for sure? Okay, fine. Nobody wants to say anything. It's okay. Just break my heart. Okay, my critical values are 0 and 4. I plug in 0, I get 0 here. Plug in 4, I get 0 here. I don't get any critical values when you do the negative x. So let's see what's doing. All right, so if I pick a number larger than 4, like 5, negative, positive. Oh, e to the negative 5 is positive or negative? E to the something is always positive, just like 2 to the something is always positive. So e to the negative 5 is 1 over e to the 5, which is still positive. So I've got a negative times a positive, which is negative. And then you can say the 4 comes from this factor with an odd multiplicity, so the sign is going to change. Or you could pick 1 and say this is positive, this is positive, this is positive. And then you can pick negative 1 and say this is negative, this is still positive, this is positive, so the whole thing is negative. Or you could say the 0 came from this x cubed factor, which has an odd multiplicity, so the sign is going to change. So our function is decreasing, increasing, decreasing. So we have a relative minimum at what point? 0 or 4? Yeah. 0, and we know that, and since it is x equal to 0, we already know the y coordinate is also 0, right? We've already found that. And we have a relative maximum at 4, comma, f of 4. F of 4 is not pretty. It's x to the 4th times e to the negative 4th, or x to the 4th, sorry, it is 4 to the 4th times e to the negative 4th, or 4 to the 4th over e to the 4th. Which actually isn't that gross of a number, because really it's 4 over e to the 4th, and 4 divided by e is less than 2, so you got a number that's less than 2 to the 4th. We could actually, so this is probably where I would get a calculator out, at least to figure out what that was, and say, okay, 4 divided by e, where are you, e? Why is the e always hiding on this calculator? Oh, there, it's okay, so pi and I, that's weird. 4 over e is like 1.5-ish, so So, sorry. And so 4 over e to the fourth is about 4.7. Okay, that's not so terrible. Okay. So that's about 4.7. Great, that'll make it not terrible to graph. Let's find the second derivative stuff. So my first derivative, and again, when I'm using the first derivative to find the second derivative, I really want it in the unfactored form. So I'm going to go back to this to write my first derivative. So my first derivative is 4x cubed e to the negative x minus x to the fourth e to the negative x. I'm going to take the derivative of this. So I'm going to use the product rule twice. This would be 12x squared e to the negative x plus 4x cubed e to the negative x times negative 1. Right, that's the derivative of just this part. And then minus, use the product rule here. We already did that one though, right? The derivative of x to the fourth e to the negative x is all of this, right? It's x to the fourth, yeah, it's all of that. So we can say, okay, well, great, it's already right there. It's 4x cubed e to the negative x minus x to the fourth e to the negative x. That's easy. Now let's put it all together. And I'm going to write the highest powers first. I'm going to have a negative, so positive x to the fourth e to the negative x. A negative 4x cubed and a negative 4x cubed makes for a negative 8x cubed e to the negative x. And finally, a plus 12x squared e to the negative x. All right, let's factor some stuff out because we're trying to find the critical values. So I factor out an x squared e to the negative x. I'm left with x squared minus 8x plus 12. And this does factor. That's why I like this problem. It actually kind of comes out pretty nicely. This factors as x. Now I'm like, how does this factor? X minus 6 times x minus 2. So we get 3 nice critical values for the second derivative. We get 0, 2, and 6. Pick a number larger than 6, like 7, positive, 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 positive. Pick a number like 5, positive, positive, negative, positive. Pick a number like 1, positive, positive, negative, negative. Pick a number like negative 1, positive, positive, negative, negative. Okay, so that means it's concave up, concave up, concave down, concave up. So it looks like I have inflection points at 2 comma f of 2 and at 6 comma f of 6. Remembering that our function is x to the fourth over e to the x. 2 comma f of 2 is 2 comma, let's see, f of 2 is 16 over e squared, which actually isn't that bad. E squared is like a little bit less than 8, so this is not far from 2. And 6 comma f of 6 is going to be 6 comma 6 to the fourth over e to the sixth, which actually isn't that big either. 6 to the fourth, oops, that's not right. 6 to the fourth.
Why is it only points 2 and 6?
Well, so when do we get an inflection point? When the concavity does what?
Changes?
So from here to here it changes, and from here to here it changes. But from here to here,
it doesn't change.
It doesn't change. So that's why we're not getting an inflection point at 0.
Okay, thank you.
I will also point out, because this is something that is almost always 100% true, you really can't have a point that is both an inflection point and a relative max or a relative min. So since 0 is already a relative extrema, it can't end up being an inflection point. and vice versa. If something is an inflection point, it can't be a relative extrema. Okay. Oh, sorry. I was figuring out that 6 to the 4th divided by e to the 6th is not terrible. It's about 3.2. Okay. So let's graph this thing. Yeah. Where I'm going to graph it right here. I'm going to erase all of this second derivative garbage. I mean, lovely work that we did, not garbage. And I'm 2, 4, 6. Okay, so here's what I've got. I've got an intercept at 0, no vertical asymptote, horizontal asymptote. We're still talking about that. We have a sign chart, we have a relative minimum at 0, 0, a relative maximum at like 4, 4 practically. It's a little higher than 4. We have inflection points at about 2, 2, and about 6, 3. Okay, and now I would like to have that. Let me pull over that first derivative sign chart just so you can have it. Negative, how is negative, right? Yeah, sure. Okay, so here's what I know is happening. I know I'm decreasing, hit that point, then I'm increasing, hit that point, then I'm decreasing. Okay, so let me ask you guys. Does the fact that I'm decreasing over here mean that I have to have a horizontal asymptote to the right? Yes or no? That's a good question. So if I didn't have a horizontal asymptote and I just kept decreasing, I would probably do something like this. But, well, one, that's the wrong concavity. It's supposed to be concave up at some point. And 2, I don't have any x-intercepts, so I can't cross the x-axis. So I'm kind of stuck. I'm kind of forced into having a horizontal asymptote, right? Concave up, concave down, and then right here my concavity changes to being concave up again. I'm kind of stuck. All right, so maybe you don't like that explanation. I wouldn't fault you for not liking that explanation. So let's talk about the horizontal asymptotes and the end behavior for just 1 second. So end behavior of this function f of x equal to x to the 4th e to the negative x, or if you prefer, x to the 4th over e to the x. Let's talk about it to the left first, because the left is easier to deal with. You look at the limit as x goes to minus infinity of x to the 4th e to the negative x, you're going to get infinity. So you're going to get negative infinity to the 4th times e to the negative infinity. Negative to an even power is positive, so that's going to be a positive infinity, and e to the infinity is also infinitely large. That's going to be infinity, which is what we see in the picture, right? As you go that way, the function's going up to infinity. All right, how about to the right? So the limit as x goes to infinity of x to the 4th e to the negative x is less clear. In fact, it's an indeterminate form. If you plug in infinity, you get infinity, and e to the negative infinity is 0. So infinity times 0 is... Sometimes infinity times 0 is infinity. Sometimes infinity times 0 is 0. Sometimes infinity times 0 is 17. It really is indeterminate, meaning it can be anything. So this requires more work. And really what this requires is L'Hopital's rule. But we don't have L'Hopital's rule. So we're going to say the following thing. I'm going to write this as the limit as x goes to infinity of x to the 4th over e to the x. And then I'm going to tell you e to the x is bigger. Right? If you graph x to the 4th and e to the x gets bigger so much faster. It is literally exponential. Super big. Whereas x to the fourth is just polynomial. And here's something that is also true. Exponential things, as long as their base is larger than 1, an exponential thing will always outgrow a polynomial thing. So even if it was something dumb, like x to the 1,000th power over 1.2 to the x, this is going to be real big for a while, right? The top is going to, right, 2 to the 1,000th is a giant number, right? The top is getting large very fast at the beginning, and the bottom is taking its sweet little time. But if you let x get big enough, this denominator is eventually going to be way, way, way bigger than this numerator, like infinitely bigger. So what I'm trying to say is that this limit is 0 because the denominator is much larger than the numerator. In the same way, this limit would also be 0 because the denominator eventually, as x goes to infinity, is much larger than the numerator. That's kind of it. And so that shows us, oh yeah, if the limit's 0, you got a horizontal asymptote of y equal to 0. Okay, f of x equal to 2. This is not a good pen. I'll ditch it in a second. Should we do that one or that one? Let's do this one. 6x to the 5/3 minus 15x to the 2/3. And I will point out that the domain of this function is everything. Right? If you've got cube roots, you can take the cube root of any number, positive or negative. So we're perfectly safe domain-wise. All right, so let's find the stuff. Y-intercept means that x equal to 0. I'm going to get 0. Right? F of 0 is 6 times 0 minus 15 times 0. X-intercepts, we need to do some factoring. So I can factor out a 3 from each of these, and an x to the 2/3. I'm left with a 2 times an x to the 1st minus a 5. And then if I set that equal to 0, I get x equal to 0. I also get x equal to 5/2. Okay. There are no vertical asymptotes because the function's not undefined anywhere. And in a similar way to, even though this isn't a polynomial, this is kind of just powers of x. And for powers of x, you typically, like, where it's just like coefficient times x to a power, coefficient times x to a power. If you just have fractional powers of x, you usually have just m behavior that's plus or minus infinity. This isn't going to be getting close to any particular number. If you really want to see what the m behavior is, it's easier to look at the factored form. If x is going to infinity, this is infinity, this is infinity, infinity times infinity. If x is going to negative infinity, this is still infinity because it's negative infinity squared, which is positive, and then the cube root, which is still positive. This is negative infinity, so positive times negative will be negative. So we know to the left, it will go down, to the right, it will go up. But we're also going to see that from the first derivative. So I don't think you need to think about m behavior so much unless it's specifically horizontal asymptotes. So horizontal asymptotes, as far as I can tell, there aren't going to be any. It's not rational. There's no e to the x. It's just gross powers of x. So let's find the first derivative stuff. Okay, we're going to need to be a little extra careful here. So let's make a derivative here. It's going to be 6 times 5/3 x to the 2/3 minus 15. I should probably write f prime. That'd be a good idea. 15 times 2/3 x to the negative 1/3. Simplifying a bit, 6 times 5/3 is 2 times 5, which is 10. X to the 2/3. And 15 times 2/3 is also 10. X to the negative 1/3. Okay, and I'm setting this in as equal to 0. What can I factor out for sure? A 10. What power of x can I factor out? The 2/3 or the negative 1/3? Well, here's the thing. Whenever you're factoring, sorry, I kind of made this look gross. Whenever you're factoring out x to a power, you are always factoring out the smaller power. And a negative thing is always smaller than a positive thing. So I'm going to factor out the x to the negative 1/3. Here I'm left with x. Here I'm left with 1. Clear? Questions? So I set this equal to 0. There's only one solution. And the solution is x equal to 1. You might be thinking somewhere in the back of your head that 0 is the solution to that, but it's not. Because 0 doesn't make the derivative 0. 0 makes the derivative undefined, which is still a valid point. Like, we're still going to include it. It's still a critical value. And the critical values are x equal to 1 and x equal to 0. It's just that this is where the derivative is 0, and this is where the derivative is undefined. Because 0 to a negative power is division by 0. Great. So the reason I point that out is because when we graph it, if we know the derivative is undefined, we know we should have like a pointy point, like a cusp. 0, 1, pick a number larger than 1, like 2, or 8 if you want to pick something that's easy to take the third root of. 2 minus 1 is positive. 8 minus 1 is also positive. 8 to the negative 1/3 is 1/2, right? It's the cube root of 8, but reciprocal. So positive, positive, positive. And then we're going to change signs because we came from this factor, which has an odd degree. So it's going to be negative here. And now we're also going to change signs because this is an odd root power thing. Or you can just plug in negative 1. Negative 1 minus 1 is negative 2. Negative 1 to the negative 1/3 power. Okay, negative 1, the cube root of negative 1 is still negative 1, and the reciprocal, which is what the negative does, of negative 1 is still negative 1. So it's a negative into negative, which is a positive. So we're increasing, decreasing, increasing. So it looks like we have a relative maximum at 0, 0. We have a relative minimum at 1 comma f of 1, and f of 1 is 6 minus 15, which is negative 9. Right? Let's maybe start graphing it. Let's see. So I've got 0, 0. I've got 1, negative 9. And is that all I've got so far? Oh, and I guess it's increasing, decreasing, increasing. Oh, and I have another x-intercept at 5/2. So I know it's increasing, decreasing, increasing. And I know it's going to do this kind of deal. Right? It should be pointy there. Now, this is probably where you actually really need also the second derivative to be able to really graph it and know what's happening. Because I don't really know that it's concave this way. Maybe it's some other stupid concavity. Sorry, not to besmirch any concavities there. Maybe it's really like that. By the way, technically, oh no, actually, so I would say I've almost drawn something here where you have a point that's a maximum, a relative extrema, and an inflection point. Because it's definitely a maximum, and at least the way I've drawn it now, although I've drawn it wrong, the concavity is changing from concave down to concave up. But there's something else about concavity that should be stated somewhere in your textbook, that to have an inflection point, the first derivative has to exist. And the first derivative definitely doesn't exist there. So that couldn't be an inflection point, even if it was where the concavity was changing. Okay, but that's not how it works. Let's find the good old second derivative. So our first derivative, if you recall, was 10x to the 2/3 minus 10x to the negative 1/3. My second, and again, right, even though I've got the factored one, I don't want to take the derivative of that. I'd rather not use the product. Well, it probably wouldn't be terrible there, but still, no. Let's just use the good old regular way. So we get 10 times 2/3 x to the negative 1/3 minus 10 times negative 1/3 x to the negative 4/3. So let's say I'm going to factor out. I'm definitely going to factor out a 10/3. I'm also going to factor out the smallest power of x, which is x to the, I know no one's going to say anything, so I'm just going to tell you. It's x to the negative 4/3 is the smallest power of x in this context. So I'm left with a 2 x to the 1. And then from here, I'm left with a plus 1. Hopefully that's clear what I'm doing, right? X to the negative 4/3, negative 1/3 minus negative 4/3 gives you a positive 1. Or the way I really think about it is if I multiply this back through, you would add those powers, and negative 4/3 plus 1 is negative 1/3. And then, yeah, all of this got factored out. The 10/3 and the x to the negative 4/3 and also just a 1. So my critical values are x equal to 0 because it makes it undefined, and x equal to negative 1/2. So let's see what the second derivative is doing. If x is 1, 1 to any power is 1, so that part's positive. 2 plus 1 is positive, so it's positive. And if we go over here, so this is where it can be a little challenging, right? If I plug in a very small negative number, let's say, right, because it has to be fractional. Let's say like negative 0.1. This part's positive, right? 2 times negative 0.1 is negative 0.2 plus 1 is positive. A negative number to the negative 4/3 power. So a negative number to the 4th power is positive. The cube root of a positive is still positive, and the reciprocal, right, because that's what the negative power does, of a positive is still positive. So it's a positive and a positive, it's still positive. That 4 there is kind of acting like the even power or even multiplicity that's making it so the sign stays the same. And then when we go to the other side of negative 1/2, since this factor has an odd power, it's going to change. Or you can plug in negative 1. Negative 2 plus 1 is negative, and then negative 1 to the negative 4/3 is still positive. So a positive times negative is negative. So it's concave down, concave up, concave up. So negative 1/2, it is changing from being concave down to concave up. So here's how this graph looks. It kind of looks like that. Where the concavity changes right there. It's concave down over here, it's concave up over there. And that point is a pain in the ass. Right? You have to plug in negative 1/2 to this. Bleh. If you do that, I don't want to do that. You've got 6x to the 5/3 minus 15x to the 2/3. I suppose it would be better to try and do it if I factored it. So I could write it like this. It's still not nice. You've got 3 times negative 1/2 to the 2/3 power times 2 times negative 1/2 minus 5. Gross. That's something. It's, I don't know. That's a negative 6 times, that's a negative 18 times negative 1/2 to the 2/3. Yeah, we'll call it a day on that one. Not like class is over, just like, I'm not going to do any more with that problem. You all watch me struggle to use a straw. I know. It's great. Should we do more graphing? Should we do something else? I can do more graphing. Let me do, I got at least 2 more graphs I should do. Let's graph f of x equal to the natural log of x squared. All right. Here is definitely a problem where it's good to think about the domain ahead of time, because here we know that for sure x has to be greater than 0. I should also point out this is not the natural log of x squared, which is 2 natural log of x, right? Very, very different than that. So let's see what we've got here. Y-intercept, well, there can't be a y-intercept because x can't equal 0. X-intercept, set the whole thing equal to 0. So natural log of x squared equals 0 means the natural log of x would have to equal 0, which means e to the natural log of x equals e to the 0, which means x equals 1. So 1 is our x-intercept. Vertical asymptote. Do we have one? We do. It is at 0. So, right, the normal natural log function has a vertical asymptote, right? The normal natural log function looks like this. As x gets closer and closer to 0, the natural log gets more and more and more negative. Here, though, as x gets closer to 0, it's going to get closer and closer to negative infinity squared, so it's actually going to shoot up to positive infinity. And then I do not believe we have a horizontal asymptote, because we know that as x gets larger and larger, the natural log function also gets larger and larger without bound. So no horizontal asymptote. All right, let's find the first derivative stuff. So take my derivative. I use the chain rule here. It's going to be 2 natural log of x to the first times the derivative of the inside, which is 1 over x. I'm going to set that equal to 0. And let's see, I get that, well, again, I get x equal to 1, right? Because I know that natural log of 1 is 0. How about x equal to 0? It's iffy. You could maybe include it, but the problem is it's kind of the end of your interval. So I don't really think you need, it's important in that 0 is kind of the end of our domain. So if I would really say this is the only critical value. Let's do our number line. And here's how I'm going to do my number line. There's 0, there's 1. 0 is not included, right? Because we don't get 0. So if you have a limited domain, I do think drawing your number line so that it reflects that limited domain is probably a good idea. Let's pick a number bigger than 1 to plug into the derivative. What's a number that's bigger than 1 that's easy to take the natural log of? This one I am going to wait for an answer for. Yeah, exactly, e. So I pick e, the natural log of e is 1, so I get 2 times 1 over e, which is positive. Okay, here's a slightly harder question, but has a similar answer. What's a number between 0 and 1 that's easy to take the natural log of? Exactly. 1 over e. Sometimes you have to do one that's smaller than 1 over e and then use 1 over e squared. If I plug in 1 over e to natural log, I'm going to write it as e to the negative 1 instead of 1 over e. And then 1 over 1 over e. I get 2 times natural log of e to the stuff is just the stuff times e. That's definitely a negative number. Negative 2 times e is negative. So my function is decreasing and then increasing. So I definitely have a relative minimum at x equal to 1, which is also where my intercept happens to be. Okay, So here's what we've got so far. We don't have a lot. We have an intercept at 1, and it's also a relative minimum, meaning we know we're doing something like that. So it's going to be, and we also know it's going up to infinity right there. But we're not exactly sure. Maybe, I don't know, maybe the concavity is something funky to the right. Probably not, because we know it's increasing afterwards. But I guess there are two different kinds of increasing. I mean, there's a lot. What I say is you can be increasing like this, so the concavity doesn't really change. I probably made this look a little too parabolic. It's not a parabola. But it could also be increasing like this. So the concavity does change. And we actually have to determine what the concavity is to know. So my first derivative was 2 natural log of x times 1 over x. Let's find the second derivative using the product rule. So let's just leave the 2 out in front. It's the derivative of that times that plus that times the derivative of that. And the derivative of that is, well, that's x to the negative first. The derivative of x to the negative first is negative 1 times x to the negative second, or negative 1 over x squared. All right. And I see that I can factor out a 1 over x squared from each of these pieces. This is 2 times 1 over x squared times 1 minus the natural log of x. Okay. You know what? It's funny. I didn't actually expect the graph to look like that, but I think it actually is going to look like that. It's kind of interesting. So we set this equal to 0. Again, 1 over x squared would be undefined at 0, but 0 is not in the domain. So I'm going to set this equal to 0, and 1 minus natural log of x equals 0 when x is equal to e, because the natural log of e is 1. So picking a number larger than e, like e squared, to see what my second derivative is doing. Oh, sorry, I should have drawn my number line more accurately. Picking a number larger than e, like e squared, 1 minus natural log of e squared, and natural log of e squared is 2. 1 minus 2 is negative. That part's positive, that part's positive, so it's going to be a negative. And then something between 0 and e, like 1. 2 times 1 minus natural log of 1 is 1, or it's 1 minus 0, which is 1. So it's positive. So yeah, it's concave up, concave down. So it totally is concave up until you get to like e. And then right there, the concave, I totally just happened to draw it pretty on, spot on. That's kind of interesting. But it still does keep increasing, right? It doesn't like ever turn around, or it doesn't even flatten out, right? There's no horizontal asymptote here. And I guess we maybe should say more about that just to be super duper clear, right? If you look at the limit as x goes to infinity of the natural log of x squared, we know that the natural log function does increase to infinity, right? If you look at the natural log function, the regular one, it just does this. Sorry, it just does right like that. And even though it slows down, it still keeps increasing. So does this. So yeah, this doesn't ever like flatten out and have a horizontal asymptote. It might look like it does, but it doesn't. It's a good example. I like that one. I know I said I had another one. Yeah, there it is. Interesting. I just got a notification that there's a comment on one of my YouTube videos, which I usually turn the comments off, so it seems weird. I'll have to go take a look and see what terrible things someone is saying about my video. Anyway, let's look at one more example, and then I think we will call it a day for real. Let's look at the function x times the square root of 8 minus x squared. Like the previous example, this example has a limited domain. Here our domain is 8 minus x squared has to be greater than or equal to 0. So 8 has to be greater than or equal to x squared. So there's a couple ways you can do this. I'm partial to saying the square root of 8 is bigger than or equal to the square root of x squared. The square root of x squared is the opposite value of x. So that means that x has to be less than or equal to the square root of 8, bigger than or equal to the negative square root of 8. And again, I think this makes sense, right? If x is between those, it's fine. Like if x is 2, great, 8 minus 4, positive. Or if x is negative 2, great, 8 minus 4, positive. But if x is 3, 8 minus 9 is negative, can't take the square root of negative. Or if x is 2, negative. If x is negative 3, 8 minus negative 3 squared is 8 minus 9, which is also negative. So we're stuck between negative root 8 and root 8. All right, let's find our stuff. So y-intercept. If x is 0, we're going to get y equal to 0. X-intercepts. So if we set the whole thing equal to 0, we can clearly see that x equals 0 is an x-intercept, as well as plus or minus root 8. Right? If we plug in plug in root 8, we get 8 minus 8, which is 0. So those are our intercepts. And then we need to find the first derivative. So, we should talk asymptotes. There's definitely no vertical asymptote. Although this function is undefined in many places, there's no places it's undefined in a division by 0 sort of way. So there's no vertical asymptotes. There's also no horizontal asymptotes for sure, because you definitely can't take any limits to infinity if your domain is between negative root 8 and positive root 8. So then let's talk about the first derivative. So the first derivative, So I'm going to use the product rule. It's going to be 1 times this, which I'm going to write as 8 minus x squared to the 1/2, plus x times the derivative of this, which is 1/2 times 8 minus x squared to the negative 1/2 times negative 2x. That's not fun. And if I'm trying to set this equal to 0, I'm going to have to factor. So I'm going to factor out an 8 minus x squared to the lesser power, which is the negative 1/2. So I'm going to say this is 8 minus x squared to the negative 1/2 times, so here I'm going to have an 8 minus x squared to the 1. And then here I'm going to have an x times a 1/2 times a minus 2x, which is going to be minus x squared. Okay, so I end up with, here I've got 8 minus 2x squared over 8 minus x squared to the 1/2. And if I suppose I could factor out a 2. This is 2 times 4 minus x squared over the square root of 8 minus x squared. So I get x equal to plus or minus 2 is where it's 0. And I do get that x equals plus or minus root 8 is where the derivative is undefined. And those are places that are in the domain, so they technically are critical values. They're real critical values. They're not like these pretend critical values. They're actually critical values. Okay, so yeah, well. A lot of I should have said this before. When I was doing that example with the 5/3 and the 2/3 power or whatever, and we had the place where the derivative didn't exist, what I should have mentioned is that the derivative not existing here and getting a pointy point like that, you can see that the slopes of the tangent lines are getting very, very vertical. And what's really happening is that the derivative isn't existing. For one of the reasons it's not existing is because the tangent line is vertical and the slope of the vertical line doesn't exist. So that's kind of what's happening. When you have a derivative not existing, it often means that your graph is behaving in such a way that the tangent line would be a vertical line. All right, so we have the first derivative stuff. Oh, we're going to make the sign chart. Let's make the sign chart. Notice I'm drawing my sign chart in a way where it's not having arrows, but we're ending at negative root 8 and root 8. And then we've got negative 2 and 2. A little sniffly. So I pick a number a little bit bigger than 2, but not 3 because 3 is out of bounds. So I'm just going to think about a number being bigger than 2, like 2.1. This top is going to be negative because 2.1 squared is bigger than 4, and 4 minus number bigger than 4 is negative. So the top's negative, the bottom's always positive because it's the square root. Negative over positive is negative. If I pick 0, positive over positive is positive. If I pick negative 2.1, it's a negative on top again over a positive 1. So I'm decreasing, increasing, decreasing. So it looks like I have a relative max at 2, or 2 comma 2 times the square root of 4 minus 8 minus 4 is 2 times the square root of 4, which is 2 times 2, which is 4. And a relative min at -2, -4. If you plug in -2, you get -2 times 2, which is -4. All right. I need second derivative, really? Really? The second derivative? Fine, the second derivative. Yeesh. Let's pretend like we didn't say it. No, okay, fine. Let's look at it this way. So let's look at 8 minus x squared to the negative 1/2. Times 8 minus 2x squared. That's our first derivative. So let's find the second derivative. Derivative of this is negative 1/2, 8 minus x squared to the negative 3/2 times negative 2x times that plus this times the derivative of that, which is negative 4x. All right, here's what we can factor out. We can factor out an 8 minus x squared to the negative 3/2. Maybe some other stuff too, but I'm going to start with that. All right, the negative 1/2 and the negative 2 cancel, so I'm left with x times 8 minus 2x squared, which I'm going to write as 8x minus 2x cubed. Over here, I factored out 8 minus x squared to the negative 3/2. That leaves me a positive one of those behind. Right, if I multiply that by that, you add the powers and you get a negative 1/2 power, so we're good. And then you get a negative 4x there. So let's see, this looks like 8x minus 2x cubed. 8 times negative 4 is minus 32x and minus, this feels like I've made a mistake, which is really unfortunate because we were so close to being done. But I've got, let's see, a plus 4x squared. Maybe not, maybe I'm just imagining things. Oh, I am imagining things. We're good. It just looks terrible. Okay, I can factor out an x from the top, and here's what I've got. So I'd probably factor out a 2x, really. Sure, let's factor out a 2x. So here I'm left with, let's make it a negative 2x, fine. So I'm left with an x squared there. For my 4x squared, if I factor out a negative 2x, I'm left with a negative 2x. And from my 8x minus 32x, which is negative 24x, I'm left with a positive 12. Whew. Okay. This doesn't factor. Yeah. In fact, this doesn't have any roots. If you try and solve this, you get nothing. So we only get x equal to 0 as a place where the concavity changes. If x is positive, like if x is 1, you get negative, this is positive, this is positive. If x is negative 1, you get this is positive, and the rest is positive, positive. So it's concave up, concave down. Ooh, that was kind of a pain. I guess we should graph it. Like this. I feel like I might have made it smaller earlier, but I know that there's no things, so anyway. Let's graph the darn thing. Okay, here we go. Here's the real exciting graph. Got 0, 0. You know, it ends at root 8. negative root 8. And I know I have relative max at 2, 4. And relative min at negative 2, negative 4. And I know it's decreasing, then increasing, then decreasing. So here's how it looks. And at the endpoints, it should look like that the tangent line would be going vertical. Concavity goes from concave up to concave down.